His Majesty's destroyer Jovial, after a strenuous period of active service, has been in for a boiler clean. Now the job's done, she's ready to sail again. Funnels are covered, boilers are cold, but soon steam must be raised. Stores, equipment, and all the 101 necessities of a fully commissioned ship are brought aboard, not forgetting a good supply of ammunition, just in case... Hello? Who's this? A Wren dispatch rider. It's a signal for the captain, so the officer of the day takes it below to his shore cabin.
Come in.
Signal from Captain D, sir.
Thank you. Tell the chief I want him, please.
Aye, aye, sir.
Come in. How soon can you raise steam?
Take about 5 hours. We're cold, sir.
Following the orders to raise steam, the watch is ordered below. 2 men are detailed to uncover the funnel, and so they enter it by a small door at deck level and climb to the top by the iron ladder which runs up the inside. Funnel guys have to be slackened. Why? To make allowance for the expansion when the funnels get hot. This gives us a good idea of the required slackness. When the cover's removed, it's rolled up and lowered to the deck to be stowed away. Here is the layout of a destroyer as regards those departments affected in raising steam routine. The steering compartment, the boiler rooms numbers 1 and 2 with their auxiliary pumps, etc., the engine room with auxiliaries and main engines whose gearing at the aft end protrudes through the bulkhead into the gear room where 2 are the oil circulating pumps, and last, the tiller flat containing the steering gear and rudder head. To the uninitiated, a boiler room just looks a maze of pipes, taps, and valves. So let's get a clear idea of what it's all about. An Admiralty 3-drum boiler consists of an upper circular steam drum connected to 2 lower water drums by nests of tubes, the whole forming a letter A. Superheaters with their tubes are fitted between the outer and inner row of tubes on each side of the boiler. We'll deal with them later. The triangle between the nests of tubes forms the furnace space. Now come into the lab and see the elementary principle. We have a top and a bottom glass vessel connected by 2 glass tubes to form a continuous circuit. The whole system is filled with water, colored water in the bottom flask to make our little demonstration more clear. Just imagine the glass tubes are boiler tubes, the inner one nearest the fire. The top flask is our steam drum, the bottom one our water drum. When heat is applied to the inner tube, the heated water rises, forming steam in the top vessel or steam drum. The water in the steam drum descends through the outer or cooler tube down to the bottom or water drum, and so we get a continuous circulation. And with that in mind, let's get back to our drawing. Note the water level in the steam drum is normal as when steaming, but when idle it should be kept full to prevent airlocks or corrosion. The water descends through the tubes furthest from the fire into the water drums. Then it rises through the tubes nearest the fire, during which course it's converted to steam and goes into the steam drum. At this stage, it's saturated or moist steam, so it passes into the superheaters, which are out of contact with water in the boiler. Here, our steam is just simply cooked, and becoming dry steam, passes on to the engines. This model boiler, with casings on one side removed, gives us a perfectly clear idea of the superheater layout. Its tubes, remote from water, are a unit on their own, running between the boiler tubes for their full length and depth. Engine efficiency depends upon limits of temperature, high when the steam enters, low when it leaves, hence superheating, which raises temperature without pressure increase and saves fuel, for less steam is required and, being dry, causes no corrosion. Here's the front view of our boiler. Study it. Steam and water drum. Boiler feet. Air cones with oil-fuel sprayers in the center. The funnel uptake. Observation window to see what's happening inside the furnace. Smoke-making nozzles through which an overdose of oil is passed on orders to make smoke. Here's what happens looking through the observation window. And here's what comes out of the funnel. But remember, a well-fired furnace should show no smoke whatever, only a heat haze. Let's take one half away. The furnace chamber has to withstand a temperature of 2,700 degrees Fahrenheit, so it's lined, both floor and side chambers, with courses of brick which won't melt or decompose. Water to the main drum is fed by an internal feed pipe. An automatic feed device controls the quantity of water which passes through a non-return feed check valve. Note the position of the internal steam pipe through which the steam passes to the superheaters. Soot doors provide access for cleaning purposes, and movable panels provide ready access to the tube nests for boiler cleaning. In this sectional drawing, we see the outer casings of our boiler in position on one side. These cases serve to retain the heat and to act as the necessary conduits for the entry and flow of air. And just to round things off, let's put the other side back, and there's the boiler complete. And so, with the principle fully in mind, let's return to the ship, for steam has to be raised in 5 hours, and there's no more time to play about with pretty drawings. There's a job to be done. This is all bilge, as it were, for the bilges, like the furnaces, have to be examined and kept clean and free of oil. If oil is found, there is danger of fire. And, well, we all know what fire at sea means. So, safety first. And it's part of the routine to make quite certain that fire appliances are all in good trim. Now for the fans, which supply the forced draft for the furnaces. They're not much like the bellows of a great fire, but that's their function. They run at a very high speed, so it's important to see that the oil levels are well up. They're checked by a dipstick, just the same idea as on a motor car or lorry engine. Now, beer won't flow from a barrel unless you open the vent. The same applies here. Air cocks on the steam drum and superheater headers have been opened so as to release any vacuum which would prevent flow. Running down hoses are connected to the running down valves. Superheater drain valves must be open and the steam trap kept on bypass. Next, the running down valves are shut, and the valves on the main steam ranges are opened and shut hand tight to make sure that all is working nice and freely. fuel oil has a very high flash point. Here's a crucible of ordinary fuel oil, cold or at atmospheric temperature. Put a light to it and it just won't burn. Well, that doesn't seem much good. So we'll warm the oil and try again. Now it's hot and ignites instantly. Remember this experiment, for that's just what we have to do in the ship. Heat the oil before it will burn in the furnace. Fuel oil is fed to the furnaces by sprayers. Here's one cut in half. It's really a valve with fine adjustment which delivers the oil in a fine misty spray, enabling it to burn easily. The sprayers are mounted on the boiler as we see here, surrounded by adjustable air cones by which the required amount of air can be regulated to give good combustion. If you were inside the boiler, here's what the delivery end of the sprayer would look like. Now, to heat our oil, a small lighting up sprayer is put in place of one of the main sprayers. Then a long U-shaped tube is inserted into the furnace, and each end of it is tapped in, so to speak, into the fuel oil circuit. A small electric auxiliary pump is started so as to circulate the oil. This U-tube works just the same way as the old Primus stove. We all know how the tube has to be heated before the fuel can be pumped up and made to burn. Yes, it's just the same thing. The fuel passing through the hot tube is rendered combustible. The U-tube is so fitted that it just touches the small end of the combustion tube. When all is ready, a handful of oily waste is put into the cone below the U-tube, and the small lighting up sprayer is warmed up and brought into use, giving sufficient flame to heat the U-tube and the oil which is circulating through it. A small thermometer shows the rising temperature of the oil. When a blow of steam issues from the air cocks, this one's blowing into what's known as a pig's ear, they should be shut. The drains on the auxiliary steam range are then shut and valves on auxiliary pumps are opened. You all know how a kettle furs up and gets scales inside it. That's due to impurities in the water. So frequent tests are made of the boiler water to ensure purity. Samples of water are drawn from the boiler into a hydrometer pot. The temperature is taken, and the water is tested for density with a hydrometer. Now a further test for salinity. To a test tube of water, a few drops of silver nitrate are added. This water is pure, nothing happens. But just let's see what would have happened if there had been salt present. A white precipitate appears, or brown if there's lime in the water, so that's why distilled water should always be used in boilers. When there's a sufficient head of steam, the main oil fuel pump, auxiliary feed pump and oil fuel heaters can be warmed through and started, not forgetting the fans which provide the air and draft. The superheater drains are now changed over to the steam trap from the bypass to avoid wasting steam. For instead of blowing it into the air by our atmospheric exhaust, we're going to put it through the cooler, condense it, and use the water to make steam again. So we put the closed exhaust onto the feed heaters. Now the oil's hot, so we can get rid of our old friend the U-tube. Lighting up gear to you. Remember that plan of the ship? Well, now we're in the gear room. Lubricating oil passes through coolers which retain it at a correct viscosity or thickness, so all inlet and discharge valves on the coolers are opened. Next, the forced lubrication pump is started and the lubricating oil circulation checked. Circulation can be watched and checked at various points by these small glass telltales. At the aft end of the turbines, there's a hand turning gear used to keep the engines free when the ship's laid up. When raising steam, the gear is disengaged, otherwise it might cause serious damage. So it's removed and taken to the engine room. Unless it was there, no engineer would start the engines. Talking of engines, let's study the principle of the turbine, for it's so enclosed we can't see much in the ship. A casing, or stator as it's called, encloses the rotor, a cylindrical drum mounted on a spindle. In both stator and rotor are set circular rows of blades. Steam is admitted at one end of the turbine and travels between rotor and casing. As it expands between the rows of blades, it causes the rotor to revolve. The turbine is mechanically superior to any known steam engine, for there is only one moving part, the rotor, and only two wearing surfaces, the main bearings. To ensure expansion and normal running conditions, before the turbines are started, they should be drained and warmed through. This man's underneath the turbines, opening the drains. The turbine is very finely and sensitively adjusted, so during the warming through, the even expansion of all parts is of vital importance. Careful observation of movement is maintained throughout, and readings are taken from the scaled finger plates. In high-speed machinery, such as a turbine, care and attention to lubrication is a matter of paramount importance. Always remember, oil is cheaper than repairs. Warming through should leave the inlet to the low-pressure turbine at approximately 160 degrees Fahrenheit an hour after steam first shows. This thermometer enables the patient's temperature to be watched carefully. Now the extractor pump is started up, and the condenser water level should be watched at the same time. Well, things are now nearly ready. Valves on the closed feed system up to the main feed pump are opened, also the air ejector. The vacuum is worked up to 20 inches using a minimum of steam, for the lower the pressure at the exhaust end of the turbine, the greater the efficiency, because the work done by a given quantity of steam depends upon the difference of initial and final pressures, that is, boiler pressure and condenser vacuum. Part of the routine in raising steam is to test the telegraphs and steering gear. In the steering compartment, the engineer officer carries out these tests, taking careful record of the readings on the graduated arc, which shows the degree of rudder on the ship. Simultaneously, an artificer in the tiller flat is recording the readings from the graduated scale on the receiver crosshead. The two sets of readings must correspond exactly. Next, the revolutions telegraph is rung down to the engine room, where the readings on the indicator must correspond with those of the transmitter. The maneuvering telegraph is also tried out in the same way. And now everything is ready for sea. The chief engine room artificer reports and asks permission to try main engines of the officer of the day, who first makes sure that all lines and obstructions are clear of the propellers. All's clear, so the chief engineer tries out the main engines. The ahead and astern maneuvering valves are worked, moving the engines a few revolutions ahead and astern. In fact, this performance is repeated every few minutes, keeping the engines warmed and drained until required for use. That won't be long.
Come in.
Engine's ready for use, sir.
Good. Ring on.
Ring on, sir.
Let go. Forward. Slow ahead port.
Slow ahead port, sir.
Half ahead both. 130 revolutions.
And so to sea. Just over 4 hours ago, HMS Jovial lay alongside, a lifeless ship. Now, throbbing to the rhythmic power of her engines, she moves to sea on another of her many duties.